Hello. So in this lecture, we're going to go through the components of Chapter 2 that cover the introduction to Chapter 6, which is on nucleotides. I believe it's Chapter 6. Sorry, just going to check really quick to make sure it's not like something else. Yep, Chapter 6. Okay, so let's first of all look at what we're looking at. And this is lecture 49, by the way. So we are looking at the organic chemistry behind nucleic acids. Okay, so this class of biomolecules. And before we get into it, let's break down the difference between some of the building blocks. So the building blocks of RNA slash DNA, and these would be the nucleosides and nucleotides. So I flipped the order from what I said. So I've got the nucleotides first. Now what these look like is they are and you've probably seen this before, so forgive me for repeating myself, but we're going to take a carbohydrate, in this case a furanose, a 5-membered ring carbohydrate. We show it as the Haworth projection. And now on the right side, we're going to have a nitrogen atom connected to something that we're going to call a base, and we'll draw that in just a second. And over on the left side, we're going up into a CH2O and then a phosphate, which, sorry for running out of room here, we'll show as this species. So this is a really a phospho or a phosphoryl nucleoside. Okay, so a nucleoside is the exact same structure, except we have a CH2 to an OH on the left side of the sugar. And then we have our same base. And then we're going to go OH and OH. So it turns out that both of these are for RNA. These are ribonucleotides and ribonucleosides. And the deoxy version would have an H at this position. Which I'll highlight with green. Okay, so that's the basic breakdown of a nucleoside and a nucleotide, which are the building blocks of DNA and RNA. And so the components of the nucleosides and nucleotides are the sugar unit. So we could say it this way: each has a sugar unit. And the sugar is either ribose, which if we draw it with a Haworth projection and we put the CH2 on the left, then it goes up, down, down, up. And really, that's the nitrogen that's part of the base. What we're considering is ribose, where we haven't yet replaced that hydroxyl group with the base. So this is ribose. And we could have also 2 deoxyribose. And that deoxy unit is the exact same Haworth projection, where if we put the CH2 on the left, and it goes up, down, down. Turns out this second down doesn't matter because it's an H on a carbon that has another H, so it's not necessarily chiral, but it's helpful to remember. And so the ribose and the deoxyribose sugars are shown here. These form the backbone component of, I'm going to change the highlighter here, of the nucleosides and nucleotides. And this position that I've highlighted in red is the anomeric OH. And this is replaced by the base when ribose is converted into a nucleoside? Okay, now let's look at the base structures. Okay, the base structures. Ooh, hang on. Let me just number these. So if that's the anomeric position, it goes 1, 2, 3, 4, 5. I think that's helpful because as we look at these structures, we're going to have a 3 to 5 linkage, and so knowing these numbers is helpful. Okay, so it starts at the anomeric position being 1, and then you just sort of count around the ring. Oh, excuse me. Okay. Now the base structures, there are two general classes. There's the purines and the pyrimidines. Okay, so it turns out that I like to learn this by, first of all, getting comfortable with the pyrimidine structure. So pyrimidine is aromatic, alternating double bonds, single bonds, and there's two nitrogen atoms that are separated by one carbon. And if we numbered these, we could 1, 2, 3, 4, 5, 6. We include the nitrogens in the numbering scheme, starting with one of the nitrogens being 1. Now the purines are a pyrimidine. Goodness, excuse me. These are a pyrimidine that are fused to an imidazole. And the book has the H sticking down. I suppose there's a hydrogen bond opportunity, perhaps, although I think that nitrogen with an NH is what's replaced with, is what bonds to carbon when we actually form the nucleosides. Okay, so we have our purines and our pyrimidines. If we count this one, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, as I'm sure you're not aware, we don't connect, as we look at A, T, G, and C, none of those just stand for pyrimidine or purine, right? That wouldn't be super helpful. So instead, there's different variants of these. So let's look at the actual bases. We have adenine, which is A. Adenine is a purine that has a nitrogen group in the 6th position, just kind of hanging off the ring, NH2. Okay. All right. So there's adenine, or A. And then guanine, it's a little bit different. I'm going to put a carbonyl in the 6th position. The imidazole in both cases is the same. But now in this purine, we're going to have an NH2 sticking out here. We're going to go with a carbonyl at this position and an NH here. So this guanine G, it matters a bit more where the double bonds are present in the structure. And so if we look at the pyrimidine, just a second, it's like a visitor here. Okay. If we look at the pyrimidines, we have cytosine, which is C. And so cytosine is where we take that pyrimidine core and we kind of we do a little bit of what's in. I'll just draw it. Okay, so we have our pyrimidine core. Now we're going to put a carbonyl here and an NH2 up here. So that is cytosine C, and then I'm going to put the last two together, thymine and uracil. So thymine is T, and T has a methyl group at this position. Then it goes into 2 carbonyls. 2 carbonyls. Now, thymine is present in DNA and then in RNA. Uracil gets used where we have the demethylated version. That's an important regulatory feature. So this would be uracil. I don't know. I know it always just kind of takes time to commit all of these to memory, hopefully talking through them. I mean, the more you practice this stuff, the better you get at seeing these structures and not being too intimidated by them. Hopefully recognizing that we have pyrimidine bonded to imidazole is at least kind of the first step. Okay. So what I'm going to do now is actually show a nucleoside and a nucleotide. So let's look at the nucleoside. I believe this is just adenosine. So adenosine is when we have the base equals adenine. Okay, so if I've got this here, just a second, let me, I'm going to draw adenosine and mute my mic just a second. Okay, so running out of room here. So I'm just going to move. All right, I'm just, sorry. A little bit of a distraction there. Okay. There we go. Adenine now is the base. Okay, so back to my pyrimidine core. So this would be adenosine. Okay. And so it's adenosine, it's a nucleoside, so there's no phosphate core. You could have adenosine monophosphate, diphosphate, triphosphate, if you wanted to consider other nucleotide structures. We could have, let's do a deoxy one. So this is a ribonucleotide. Let's do a deoxy. That's a ribonucleoside, excuse me. Let's do a deoxy nucleotide. I suppose I need the word ribo in there. Okay, so if we have a deoxynucleotide, we've got a phosphate core. And then I just really like adenosine just because it reminds us of the effects of caffeine, because our body blocks, uses caffeine and blocks adenosine receptors, which is a good signal for when we should rest, but we have chosen to block those with caffeine so that we can kind of keep chugging through the day. All right, looks like I'm drawing deoxycytidine, which has cytosine as the base. So this is going to be 5, and they call this the prime carbon, just because there's a lot of carbons here. 5 prime. Ooh, I forgot an oxygen here. Excuse me. Oxygen goes right there. 5 prime. And we put the phosphate at the end. Sorry, I'm getting this name wrong. It's 2 prime deoxy cytidine. And then it's 5 prime phosphate. Okay. So we have some examples of these structures, and all of the structures are listed in the book. Now, these are the components that we use to make RNA and DNA. And this, we're not going to spend too much time actually talking about genetics, RNA, DNA, double helices, the transfer of genetic information in this class. Rather, we want to focus on the organic chemistry. But now that we've come this far, let's go ahead and just draw a phosphodiester. So nucleoside tides, that is with a 5' phosphate. And again, the reason why we have the prime there is because we have carbons from the base. So we have to try to distinguish the 5 carbon on the base versus the 5 carbon on the sugar. So we call it on the sugar when we call it the 5' carbon. So we have the nucleotides connect using 5' to 3' phosphodiester linkages. And these phosphodiesters are phosphates with 2 R groups. That's what a phosphodiester is. So if we had our phosphate here, we would have R here, and then negative here. So we have a phosphomonoester in the nucleotide by our connection to the 5' position. Now what I'm going to do is just abbreviate the base structure. And so let's go ahead and consider, just to make our lives easier, just the deoxy version. Okay, so here is my deoxynucleoside. Now what I'm going to do is convert that into a nucleotide by putting a phosphate group here. Okay. And this is a base. All right, now what I'm going to do is kind of carefully drop this, just go down from the OH down below and go into an O that is attached to a CH2 that goes into the rest of my sugar. And I have another OH and then another N base. Okay, so what we're going to do is draw the phosphate. But instead of having 2 O minuses, we're going to have 1 O minus, and the other O on that phosphate comes from connection to the lower O on the upper phosphate. So if you look at our deoxy sugars, we actually don't have free OHs on the sugar backbone of our deoxynucleic acid after the nucleotides have bonded together by way of the phosphodiester. So there's my phosphodiester linkage. Now it occurs at the 3' and the 5' positions of the sugar. If we count off, we have 1, 2, 3, 4, 5. And all of these are primes because the base has counting. So there you can see the 5' connection. And then that connects to the 1', 2', 3' connection of the upper sugar. So the 3' and the 5' connection for our system. Okay. So there's how DNA polymerizes to make our nucleic acid chain from the nucleosides and the nucleotides. What I'm going to do is just scroll up and let's go ahead and look at hydrogen bonding in the DNA double helix. This is going to have, this is what's called nucleic acid complementarity. Okay, nucleic acid complementarity. All right, so you probably recall we have G and C, these pair up. A base pair. Now the reason why they pair up is all due to hydrogen bonding. Okay, so what we're going to do is consider, just want to make sure I understand this. Yeah, okay. Let's go ahead and draw G. I'm going to draw it upside down because that's how the book does it, and I don't want to make a mistake. Gosh, I did not leave myself very much room, did I? Because I have to draw another base over to the side. Here. This is actually a carbonyl. Okay. I'm going to draw these H's more explicitly. Now this R group on both of these is going to be the rest of the nucleic acid polymer chain. All right, now we're going to go carbonyl up here. And this is going to connect with C. Let's get these names down. Guanosine and cytidine. Now here's the rest of the chain going this way. Okay, so what we actually get is an opportunity to form hydrogen bonds at 3 positions. Okay, we have the NH2 to the carbonyl, the NH to the N, and then the NH2 to the other carbonyl. And so we have our 3 hydrogen bonds. And these hydrogen bonds are enough to zip these 2 bases together, assuming that the other nucleotides in the nucleic acid can also hydrogen bond with each other, and that would be the AT or AU base pair. Okay, so let's consider those structures. So we have R. Okay, this is adenosine, my favorite one. Now, that's going to have a hydrogen bond with an NH off of the carbonyl of the pyrimidine. And what's not to like about adenosine? It's just super versatile. It can form base pairing with 2 different bases, right? And so we could have the AU pair down here. Just gives us more opportunity to draw adenosine per tuition dollar. Okay, so there is adenosine. Okay, and now we have to do thymidine, and thymidine just differs by uracil just differs by the lack of that methyl group. So this is otherwise going to be the exact same. Now, what I want you to notice about the AT and the AU Oh, and this is uridine. I keep mixing up the bases and the nucleotide names. Okay, so the key thing I want you to notice is that AT/AU pairs only form 2 H bonds. And so this is a weaker base pair. And so what you'll notice if you have to do a lot of molecular biology where you're designing your own primers and that sort of thing for polymerase chain reactions, as you design those, you need to have a strength of base pairing. They call it the melt temperature. And what you do is you try to maximize some GC pairs, GC per AT/AU pairs, so that you get a stronger complementarity, a stronger double helix that will form in as your primers sort of, not a double helix, a stronger, annealing, where the 2 chains come together at their complementarity points by way of hydrogen bonding interactions that we've just talked about. If you increase the number of GC pairs, you strengthen that bond, that interaction, because more GC interactions means more opportunity for 3 hydrogen bond connection points as opposed to only 2, which is a bit weaker. Anyway, interesting things like that emerge on the grander, broader scale at the nucleic acid double helix level, which I've always thought was pretty interesting. Okay, anyway, that'll do it for this introduction. Hopefully we've gotten a little bit more comfortable with the structures. Again, we're not going to be doing molecular biology so much as we are going to really, I just want to focus on how are these things made, processed, metabolized, digested, and then what are the organic reactions behind the scenes that govern a lot of the metabolic pathways involving nucleic acids. That's what I want us to focus on. So don't think too much about, okay, it's A and it's T and it's sometimes U. That's not what we're worried about here. I just want to give us an introduction to nucleic acid chemistry, thinking about the structure of these things in the broader context too. Okay, so we'll see you next time.